Okay, so let's continue our problem. Okay, so the next step is to solving for I sub 2, right? So I sub 2, again, this is I sub 2. This is the centroid, and if for the centroid, this will be our equation, 1 over 4 pi r to the fourth. However, in this problem, our axis of rotation is along here. So therefore, the distance from this axis to the centroid, 75 mm. So we have to take into account we have to take into account this condition, and we need to apply the parallel axis theorem. Okay, so right here we have to use I sub 2 is equal to I sub x, the moment of inertia along the centroid, plus the area times the distance. Okay, so what is this? I sub x along the centroid, this is just simply 1 over 4. And so 1 over 4 times pi r to the fourth. Okay, plus the area. What is the area of the circle? It's just simply pi r squared, right, times the moment arm, y squared. Okay, so 1 over 4 times pi times this is 25 mm to the fourth, right, plus pi times 25, I think this is squared, sorry, this is squared, times the y, this is 75 squared. Okay, so what you get is 11.4 times 10 to the 6 mm to the fourth. So therefore, the total I is, I is just simply the moment of inertia of the rectangle shape minus the moment of inertia of the circular shape. Okay, so this is 112.5 times 10 to the 6 minus 11.4 times 10 to the 6, and this is in mm to the fourth. So our answer is 11.1 times 10 to the 6 mm to the fourth. Okay, so if we are going to review what we did is, this is a composite shape. So whenever it's a composite shape, meaning it's composed of regular basic shapes, then we don't need to go through the integration. And so first what we did is to draw it separately, and we found out that the total moment of inertia is simply the moment of inertia of this shape minus this shape. Okay, so we solve for the moment of inertia of 1 of the area 1, and then we solve for the moment of inertia of the area 2, and then just simply subtract it. Okay, so I think that's all for this moment of inertia. The next geometric property that we'll discuss is, it's still a moment of inertia, except that we are going to refer to the polar moment of inertia. Right, so the polar moment of inertia is, if we have this let's say we have this arbitrary shape, and let's say this is the centroid, and if we consider a differential area right here, and that distance, the distance from the centroid, let's write first the axis. We have x-axis and this is y-axis. Okay, and we said that if we are going to rotate this area in the x-axis, right, so something like this, we are going to rotate it, right? So if we are going to rotate it that way, what we need is this distance, right? So this is our y. So that's why our moment of inertia along x is y squared dA, right? But if you want to rotate this along the y-axis, so this will be the example, right? Okay, so if you are going to rotate it that way, the distance, what we need is this distance. So this is x. Actually, that's the distance to the centroid. Okay. Now, this polar moment of inertia, the distance being considered is actually this distance, the radial distance. Right? So this radial distance, let's refer to it as rho, and this polar moment of inertia, this actually comes into play when we're dealing with torsion, okay, torsional members. And recall that torsional members are just simply members in moment, except that the axis of rotation is along the longitudinal axis. Like for example, I have here a shaft. Okay, so if I have here a shaft, and let's say this is our cross-sectional area, right? So this will be our x, this is our y, and this is our z. Okay, so for polar moment of inertia, or for torsion, it's still a moment, except that the rotation, right? This is it. So it's a resistance to rotation along this longitudinal axis. Okay, so this is the rotation, direction of rotation. Whereas this one, the direction of rotation is along x, right here, and this one is along y. Okay, so except that this rotation has a specific name, and that's for torsion. Okay, so if that's the case, then if we write the moment of inertia along the y, which is x squared dA, you would notice right here that if this is our centroid and this is our area, differential area, this distance, right, this rho distance is related to the x and the y. Okay, so for the y, right, this is our y and this is our x. So therefore we can write that rho squared is equal to x squared plus y squared. So something like the Pythagorean theorem, which comes into play whenever we deal with right triangles. Okay, so generally the polar moment of inertia is measured in terms of j. J is equal to the integral of the moment arm distance, that's a rho squared, okay, times the differential area. Okay, so if we apply this, or if we substitute this relation, what we get is x squared plus y squared, right, dA. And if we distribute, what we get is x squared dA, okay, plus y squared dA. So what is this? What is this x squared dA and what is this y squared dA? This is just simply the moment of inertia along the y and the moment of inertia along the x, right? So therefore you can obtain this polar moment of inertia if through this value ix and iy. Although the same with the moment of inertia along x and y, you can use equations. You can use equations, and you can also use tables. All right. So for now, let's just leave it for now. But that's the main concept. Okay. So another geometric properties that we'll encounter is the actually there's still many others, like for example the radius of gyration, and also the section modulus, which is just simply I think it's you can just derive this using the moment of inertia. Okay, but here let's try to explain this radius of gyration. Okay, so radius of gyration, the unit of this is in terms of meter, and it is another way to represent the moment of inertia. Okay, so the radius of gyration from the word itself is just a unit of length. So what that means is, for example, I have this arbitrary area, and let's say this is my centroid, x and y. Okay, so let's say this is the total area. Okay, so what would be the farthest distance from the centroid if I take all this area and then concentrate it away from the centroid? Okay, so it's like this. Okay, so if this is the centroid, still the centroid, right? So what's going to be the farthest distance? R, or sometimes they use the symbol K instead of R. Okay, so this total area is the same total area for this. Okay, so what that means is that we have this I sub x right here, and the moment of inertia, the I sub x of this shape must be the same. So if that's must be the same, then we can actually write the distance, this distance, r squared times the area, right? So if I take the r squared, what I get is ix over a, or r is equal to simply the square root of I x over a. And if we are referring to the moment of inertia along x, then this must be along the x as well. So what that means is the radius of gyration can also exist in rx, ry, or let's say rz, or I don't know if that's the polar, right? So that's another way of representing. Now for the section modulus, this is actually a unit of meter cube, length to the cube. Okay, because this let's say s of x is just simply the moment of inertia all over the distance from the neutral axis. Okay, so if there's an x, then there'll also be section modulus for the y. Okay, so I guess that's enough for this geometric properties, and because we will solve also a lot of this when we get to the topics of flexional members and maybe torsional members, or the computation would just be the simple computations. Okay, because I assume that you have already taken this in your engineering mechanics course. All right, so I guess that's all. So we'll move on to the next topic in the next video.